Hola, I am José López, and I'm going to give you the talk about MEG and EEG source analysis. We are going to begin our talk explaining what an ill-posed inverse problem, how the way of solving this kind of problems is including prior knowledge, and we will see the prior knowledge that popular algorithms usually do. Then we will see a way to validate these possible solutions and choose the best one. So the forward problem is characterized by having some neural activity inside of the brain and trying to observe that activity with sensors at scalp level. So the first thing that we need to do for that is to understand which is the propagation model. For that propagation model, we need a head model that encompasses the conductivity and geometry of the head. So if you have that, you can create some lit fields. Then I will explain that in detail. But these lit fields will give us a prediction of what's going to happen at sensor level. Either magnetic or electric, because it's an electromagnetic field, right? So the problem that we have, the forward problem, it's the analogy will be that you know what you have in the brain, you know how it propagates, so it will be quite easy to see what's going on at scalp level. But the inverse problem only provides the information at scalp level. So we don't know which are the sources inside of the brain that are creating this activity. And we don't know which is the propagation model for these sources. So the analogy in this case will be that we know what we have as a result, but we have no idea of the other variables. So we will have infinite possible solutions for this problem. However, an inverse problem is not that difficult. It's complex, yes, but it's not that difficult. So think about this picture of Casablanca movie. Think that you are an alien from another planet and you are studying the Earth. And you receive this 2D image from a 3D space. So what's the problem? The problem is that you don't have enough information to know if, for example, in Earth, there are giant people. So you may say that, okay, people has barely the same size and planes are huge. But you can also say, no, there are giants and there are small people. Or maybe you could say, okay, this plane is not that far, so the plane is actually small because I don't know what it is. So see that if you don't have prior information, you have no idea of which of these scenarios is the true one. So the same happens with the inverse problem with MEG. You know that something is happening inside of the brain, and what is happening will create a measurement. Then you need to solve the inverse problem, and you need some prior information that will tell you what is going on inside of the brain, the current density estimate, what is the activity inside of the brain. And with that activity, you could solve the forward problem, and with that, you could have a prediction. And the question will be, is the prediction accurate with respect to the measurement that you acquired? And that is what we are going to do. So let's go to some math. So the brain activity comes from neurons. 95% of the neural activity that we can measure with MEG or EEG comes from pyramidal network neurons at the cortex mostly. So if we have a head model, we can propagate that through lit fields, and we can record the MEG and EEG activity with both devices, right? And we can take that to a mathematical model that will tell you that the data that you have can be obtained from a head model multiplied by the activity that is propagated through that head model, and of course, we always have noise. So how is this head model created? The neural activity is usually explained mathematically as a current dipole. So around 10,000 cells could be one single dipole that work synchronous inside of the brain, and that activity in the brain will be propagated through the head, achieving the skull, where you have 3 layers usually. This is the model that we usually use, and each layer has a different conductivity, so we have to go through them. The conductivity is more important for EEG than for MEG, because the magnetic field is not that affected by the conductivity. So we will have two possible solutions for this. The first one is the parametric. Let me explain the parametric one. And say that you have the activity in this location. You have around 10,000 neurons in here that will create one dipole. Usually those dipoles, we have some restrictions. One of them that we know is that the dipole is usually going orthogonal to the cortical surface. Then you have the cerebrospinal fluid. The propagation will go through it, and it will reach the first layer of the skull. Then it will propagate to the second one, and then it will reach your sensor. So you will have some activity at the sensor that depends on what is going on at cortical level, right? And the parametric solution will tell you, okay, I have this source, and I will start moving this source through the cortical surface. I want, so we can restrict the solution just to the places that we think the neural activity will go. I will talk about that later. So I can move that to another location. And what's the problem of the parametric solution? That if I move it a little bit, I put my sensor in here, then maybe it will propagate in another direction. So the activity from this new location, this is location 1, this is location 2, and the activity from location 2 could be really different from location 1. So this is what we call about a non-linear solution. I don't like non-linear solutions, so that's why I usually don't work with parametric solvers like music, for example. So I prefer working with a gain or Griffith matrix, a distributed one, which means, okay, I will have possible dipoles. All my possible dipoles will be mathematically explained. So the problem is that if I have all those dipoles to all those sensors, what I do is that I see the propagation from one dipole to all sensors, right, through the head. What is the advantage of doing this? The advantage is that if I have some activity in this dipole, I will have the response for it, or the propagation to the sensor. If I duplicate the magnitude of that activity, given that the brain doesn't move, at least in short term, so if you are still, the brain doesn't change, the skull doesn't change, because we are talking about seconds, minutes, and the propagation goes almost at the speed of light, we will say that we will have twice the amplitude at the sensor. So this is linear. The problem of nonlinearity comes when you move your dipole, but we are not doing that. What is the disadvantage? That I have thousands of dipoles propagating to hundreds of sensors. So at the end, the lead field matrix, which is constant, is fixed for a subject, will be of a number of, for example, 300 sensors to a number of dipoles, which are in the number of thousands, right? Even if you have EEG, maybe you have only 64 sensors, right? So you have few sensors and several dipoles. What will happen with that? So given the forward problem that we have, what we need is to find the, what we need is to find the neural activity, J, right? So what we do is to clear J, neglecting noise, I will talk about that later, and we take L to the other side, and we have the matrix that we have here in the middle. And that will tell you that if you have the inverted propagation model, and you have the activity that you acquire in the sensors, you will know where and how the neural activity behaves inside of the brain. The problem of this is that it is ill-posed. As I told you, you have thousands of dipoles and hundreds of sensors. So that matrix is not invertible. You have infinite solutions. So how can we solve that? We are going to solve that using the Bayesian formulation. In the Bayesian formulation, we have to include prior information. So you have the data, which is constant because you already recorded it. You have a propagation model that it's already fixed and it depends on the structure of the brain. So your only unknowns are the neural activity and the noise. So what we do is that we say, if I have no idea what is going on, I can say that usually the world behaves quite Gaussian. So I'm going to say that J is a random variable, normal, with zero mean and variance, prior variance Q. So I think that this zero means that the brain is by default off. So nothing is working unless it needs to work. That's the zero mean. And the variance means how it is working. And the noise, you will say that in your sensors, because this is sensor noise, in your sensors, zero mean, so the sensor is off unless it is getting information, but that information comes from a sigma epsilon variance, so you have some sensor noise. And with that, we can have a better estimate of the posterior activity given the data. That's what we are looking at in here. And it can be obtained from Bayes' theorem from the activity given the data. So this is the forward problem that we can adjust with the data. Our prior information, which is this Gaussian with zero mean and Q variance, and the evidence. We don't have the evidence, but given that the data is already recorded, the evidence is constant, so we can sort of neglect it. And with that, we can solve the Gaussian problem, the inverse problem, the Bayesian problem for Gaussian assumptions, which is that we can have the mean of this probability or the estimated value of J, right? And it is solved with the maximum likelihood equation, which is pretty common in statistics, physics, engineering, several fields. I want to explain you this equation, but first look that all the prior information is embodied in Q, in the Q matrix, the variance of the prior of your activity. And that matrix will be the key of what we are doing. But first, let's think about this matrix. I will give you some tips to understand it. It's not that difficult as you think. Look at this. What happens if I have no noise? So if I don't have noise in my environment, it will mean that my noise variance will be zero. So out, right? Then I will say that I don't have no prior activity. So if I have no prior, I will say that Q is the identity matrix. So it means that all my possible sources could be active at the same time because I have no idea which one is the active one and which one is the off. So what happens if I replace by the identity? J will be L transposed, L transposed, inverted by Y. And this is what we usually know as the Moore-Penrose pseudo-inverse. The Moore-Penrose pseudo-inverse is the way of inverting non-square matrices. Why is this important? Because the Moore-Penrose pseudo-inverse is non-informative at all. What we are doing is that we are including information about noise and we are including information about what is going on inside of the brain. So we are trying to be informative. That's the difference between the simple pseudo-inverse and what we are doing. Okay, so how can we estimate the prior noise covariance? And the solution is simple. We have two options. If you, for example, are using MEG, one way will be to record empty room activity that will look like that. Or if you are using an EEG or you are simply not interested in doing that, you can say that you have a regularization parameter by the identity. What does it mean? It means that your solution is IID, identically, independently distributed noise. So the noise in the sensors is random and the sensors are not related to each other. So one sensor is not generating noise in the other sensors, right? Okay, and this hyperparameter, there are many ways of finding its true value depending on the noise level. For example, cross-validation is the usual one. Now, for the prior covariance source activity, in the 80s, they defined the minimum norm. This was the first, I think the first paper is from Matti Hamalainen. And what they say is, okay, we don't have information about the brain, so I will say that the inverse problem is an identity matrix. It means that the dipoles are not related to each other. So the activity in one part of the brain has nothing to do with the activity in another part of the brain. And initially, I will say that the whole brain is active, so non-informative. And that was the first solution. Then, quite better solution was the older Loretta-like algorithms. They say that your activity is smooth. So what they say that you have the brain and you have your activity in here, but it doesn't come alone. The brain doesn't work like that. The brain says that if this part is active, you will have a region around it that will get active too. And they say that it could come quite Gaussian, right? So what we see in the dipoles is that if this dipole is active, so the dipole close to it will be active too, but with less activity. So we see a smooth solution. Then some other more informative algorithms came. It's beamformers, for example. The difference between Loretta and beamformers is that Loretta comes from a mathematical prior, and beamformers come from data prior. What beamformers does is that it takes the data and propagates it through the brain to see what is going on. And it will tell you, okay, this is the region of the brain that is active, or that a priori I think that it's active. That's what beamformers does. So the question is how these priors work. What they do? What do they do in our model? So let's see this illustrative example, and I say I have some measure activity. And a priori, I will say, okay, I think that this activity is located in this part of the brain. So let me explain you the Q matrix, how this works. The Q matrix is a number of dipoles by number of dipoles. So if I have 5,000 dipoles or 5,000 possible brain locations, that could be active at this moment, my Q matrix will be 5,000 by 5,000. It will be huge. And it will say that the diagonal matrix, each value at the diagonal matrix will mean one location in the brain. So if I activate only one value in this diagonal, I am activating only one value, only one possible location in the brain. So I solve the inverse problem with that location, and we see that that location is active, and we then solve the forward problem to find a prediction. And my question is this accurate? And if I do this just putting anything random, it won't work. As you can see, the predicted has nothing to do with the measure field. So I need more information. If, for example, I know exactly what I'm looking for, I will see that this location that corresponds to this part of the matrix will create this brain activity. And when we solve the forward problem, you will see that the prediction is quite accurate. You say, okay, I got it, but I cannot ask you to know what is going on. If you know what part of the brain is active, you won't need to solve the inverse problem. So what will happen is that you will have several dipoles, and you need the algorithm to find which one is the correct one. So the nice thing with these algorithms is that if, for example, you have run activity, look how that activity disappeared when you solved the inverse problem, because the prior didn't work, and the only one that survived was the good one, right? The problem is that in practice, you won't know which are the possible regions, so you will need to use something like minimum norm. As I told you, minimum norm says that everything is active. And the problem with minimum norm is that it will give you a large location, a large propagation of your activity, and it will tell you that although it is quite accurate, you won't know exactly where your activity is. You will have the region where it is. So if you, for example, you use beamformers, it won't tell you exactly where it is. Don't think about that, because you have noise. So you have this, and all those possible locations of variance, which is what you're looking for, they will tell you that you may have activity in here, in here, in here. You will have several parts, but the nice thing is that the inverse problem will clean most of them, and then you will have a good prediction, sorry. And you see that the propagation of the activity inside of the brain is not that large as with minimum norm. So you can also add fMRI information, for example. So if I have an image and that image says that this is the possible region of the brain, you can use that as a prior, and maybe you will get the same activity, the same activity that will happen with MEG or EEG. Why maybe? Remember that fMRI doesn't look for electromagnetic activity, and the electromagnetic activity and the fMRI prior are not exactly the same. So you cannot say that they will go exactly to the same location. Okay, so as a summary of these solutions, you will see that all my PhD was on this field, and I studied more than 20 algorithms, 20 solvers for the MEG-EEG inverse problem, and all of them were based on finding the best prior for this Q matrix, the prior variance of what I think is going on inside of the brain. So in SPM, we have implemented the minimum norm, a Loretta-like one. Loretta is free. We constrained that, and our smooth is different, but it's quite the same idea. We also implemented the empirical-based beamformers. The difference between the original beamformers and this one is that we have some tips to solve this problem. If you have activity, for example, auditory activity, it will give you two sources, at both sides of the brain. Given that they are synchronized, the variance that they provide is the same. And that will mean that for the simple beamformers, you will have either only one of them, the strongest one, you will see only one of them, or maybe you will see a source in the middle of the brain instead of the two sources that you had initially. So that's what it works. And we have a fourth one, the multiple dispersed priors, that I will explain later. So what I would recommend you to do is first try with the traditional ones and see if everything looks correct, right? If you are looking for some visual activity, you won't expect that activity in the frontal, right? And then you will go further with these algorithms. We are not the only ones who do this. So Vladimir developed this toolbox for SPM, where they have several related ways, and you will have more control of what you are doing. I also could help you with more control directly with SPM, with the codes. I will talk about that later. But for example, Field3, Brainstorm, MNE, EEG Lab, all of them have different solvers that you can use. And my suggestion will be, don't use just one. This is quite guessing sometimes, and the best way of validating is doing it with different solvers, with different softwares, and you will have robustness. Okay. So as a summary of what we have up to now is that we know that the MEG-EEG inverse problem requires prior information. And that prior information comes from the source covariance matrix. The different algorithms that you will saw, the only difference that they have is the prior source covariance. They use a different prior for the source covariance. It's the only difference with all these algorithms. And historically, every group has a name for them, usually her ex-girlfriend, I guess, because they are all feminine. Okay, so now the question is, if I have all these possible solutions, how can I choose the correct one? So let me show you this example. In here, I will choose again this incorrect prior, and that incorrect prior gave me this predicted data. And what I'm going to do, this prior is Q matrix, right? What I'm going to do is to see the variance explained by this predicted data with respect to the measured one. And you see that variance explained was awful. What happened if I know the ground truth? If I know the ground truth, so I can have a really nice variance explained, a very nice prediction. However, it wasn't 100%. Why? There are two reasons. The first one is that you have noise. You have environmental noise, you have eye movement, you have everything to make this happen. The second one is that maybe, for example, this and this activity are actually two small sources. They are not what you are looking for, but they provide information. And if you don't relate them, if you don't include them into your solution, you will lose some variance. Neither of these will be what you are going to do. You are going to use, for example, beamformers, and beamformers will give you a really nice solution. Or you are going to use minimum norm, and you can see that minimum norm has what I told you, a large solution. Beamformers is not that big, but they are larger than the ground truth, actually. So the question is, how can I choose the best one and see how the variance explained is not good for us, because actually minimum norm had more variance explained than the ground truth. So only the variance explained is not a good solution. So just looking for the error between the predicted data and the measured one won't give you the best solution. So how can we solve this problem? We suggest you to use the negative variation of free energy. I told you that we don't have the evidence, but we can get close to it. First, it's the log evidence what we are looking for. And the log evidence can be explained with two elements: the free energy F and the Kullback-Leibler divergency, KL. So the divergency, KL, is always positive or 0. And it will be 0 if your prior and your posterior, look that I have a prior on H, my hyperparameters, and my posterior comes when I use my data to fit those hyperparameters. So if the prior Q, which is the ground truth, and the posterior, which is what I did, if they are the same, KL will be 0. So KL will be higher if the difference is large, and it will be 0 if they are exactly the same. And the free energy, it's what you have left, right? So you can fit the log evidence trying to reduce the Kullback-Leibler divergency to 0, and there are many models that work with the divergency. We prefer to maximize the free energy. The higher the free energy, the lower the KL, because the log evidence is constant. This is constant. So if the evidence is constant, I will try to minimize the divergency or maximize the free energy. We chose to maximize the free energy. And what we are doing is trying to fit both models, the ground truth and the prior. So what we do is that we create our own prior and we estimate the hyperparameters, trying to get the best of it. However, we are working with Gaussian assumptions, and the world, unfortunately, is not Gaussian. So the world could be like this. Could be a bi-Gaussian, for example. Fortunately, it's not usually like that, but it could be like that. So our solution, we don't want to fit to a local maximum. We want to try to fit the whole model, and that's what we try to do with free energy. So if you want to go to the math, there, in my thesis, I decided to play with that, so we can talk about it, and we can I can explain you how to get to this. But if you prefer not to go to the math, and the free energy is quite large, as you can see, I can give you a better solution. I can explain what happens at each of these terms. So the first term, what it does is that it looks for the difference between your variance and the data variance. So we are looking the variance explained, right? And we want to minimize your data variance, your model variance. Why? Because nature is quite efficient. So one of the priors that we usually use in physics and engineering is that the best model will be the one that needs less energy to get a solution. That's why we do that. And the third one only comes from the number of sensors and then the number of data samples. So that one could be constant for us, no problem. And that's the accuracy. That's the accuracy that we want to increase. We want the higher accuracy that we can get. But for that accuracy, we have some hyperparameters that we have to fit. And we want to see the difference in variance between those parameters that we had at the beginning and the ones that we got at the end, and their sizings, the difference in size in variance. So the error in hyperparameters or the error in covariance of those parameters. And that's the complexity. And we want to reduce the complexity with the simplest model to solve this. Actually, free energy is not a strange advance or something that we got from nothing. No, actually, the accuracy term is the same for many models coming, I guess, from Akaike. The Akaike information criterion in 1974 has exactly the same accuracy term. What changes is the complexity. Akaike, the Bayesian, a linear function, there are many complexity models, and we just use another one that we like. And the complexity is the key of what we are doing here with the brain, but I will try to explain it to you with something simpler. I want to explain it to you, just estimating a linear regression, a polynomial regression, sorry, for this estimate. You see that it's noisy, it's quite real, and what we are going to do is to see how the accuracy and complexity have a trade-off. So look that if I go to the first degree, not accurate at all, I have high RMS error. But if I use a quadratic equation, that will get better. You see that it fits better, but not good enough. If I go to a third degree, I see that it fits really well. So the RMS error continues going down, but I want to see what happens later, and I see that the fourth degree is almost the third degree. So look how the RMS error didn't change at all. So the accuracy didn't improve. However, I went for a 20% increase in complexity. Why? Because I went from a third degree, it was A0 plus A1x plus A2x squared plus A3x elevated by 3. But what is the problem? This is with 3. When I go to the fourth degree, I have the same plus another term. So I have to find another variable, right? I'm increasing in 20% the complexity of the problem. So the free energy will highly penalize the fourth degree and will tell you, no, keep the third degree, because the accuracy didn't improve, but the complexity highly affected our model. So we are going to the hyperparameters, which are the A's in here, and we are going to say, we are going to penalize that, right? So go to our problem. The incorrect prior shouldn't be a problem, but remember that the ground truth didn't have as high as a good variance as we had with beamformers and minimum norm. So let's see, and the free energy, the log model evidence gave us higher free energy for the ground truth than for beamformers, and beamformers, which is more informative than minimum norm, had actually higher free energy than minimum norm. So for us, free energy works because we know that it will give us better, it will penalize the complexity, for example, of the minimum norm. Why minimum norm is so complex? Because it says that the whole brain is active. So there is a huge effort to find the correct sources. Beamformers doesn't have so many, but the ground truth only have your ground truth. So it will ignore quite some of the noise, and it will tell you the free energy is higher than other models that have more noise, right? Okay, so to finish this talk, I will present you the multiple express prior solution, which is the one that we prefer you to use and we developed. This solution again goes to the Q matrix, but we have a different perspective for this. We say that the Q matrix is created but by the sum of many priors. So you have many possible priors. And what we do is that we weight them. Each of them is weighted depending on how plausible it is. So for example, this one can be a minimum norm prior. You can have an fMRI prior. So what we are doing is that we are embodying all these priors. We are including all the prior information that you may have. I have a guess. I think that it is temporal. Okay, include the temporal lobe. You can include everything in there. And then we are going to use an algorithm to find, by maximizing the free energy, we will start discarding the priors that are not good and selecting the ones. So how does it works in practice? For example, the normal model in SPM has 8,000 dipoles. So we get 8,000 dipoles for the possible locations of the activity in the brain. All these dipoles are in the cortical surface. So for example, if you are looking for activity in the cerebellum, that won't work. Don't worry. You can ask us and we can help you creating a model that will include dipoles in the regions of the brain that you're looking for. We have done that before. But normally we say that 95% of the brain activity comes from the cortical surface. So that's what we do. And we choose approximately 500 of them distributed randomly at the head, at the brain, sorry, at the cortical surface. And each of them, it's quite a small Gaussian bell with 1 centimeter in the brain. So what happens? You have your brain, we choose one, and we say, okay, I will smooth, like in the Loretta-like solution. I will smooth because I know that the activity around it will be active. And then we find another one, and we smooth it, and another one, and smooth it, and we do that for 500 times. And each of them, it's a D matrix, right? Each of them will create 1D matrix. We can also include, for example, fMRI priors, and each of them will be its own D matrix, and we will have hundreds of possible D matrices that we are going to optimize to find which are the ones that will survive, right? And that will be the posterior activity that you will have. So how does it work? It works with an iterative algorithm that maximizes free energy, and it will start with a ROM prior, but it will start pruning the possible locations. And once the iteration goes, so you see that you have more iterations, the complexity will go down because the model will be simpler than the original one, and the accuracy will go up. Once the complexity stops moving and the accuracy stops moving, so given that the free energy is the trade-off between accuracy and complexity, you will have a maximum. So when the free energy stops moving, it will say, okay, I have the correct answer. And that's what you are going to have at the end. So as a conclusion, we have seen that we can solve the inverse problem, but only with prior information. You need prior information to solve any inverse problem, not only the MEG or EEG. And for the solutions that we are working in here, we work with the maximum likelihood solution, which is known in control systems as the weighted sum of it works with simple models. And the source covariance matrix is the key. It's the only thing that you work with. So you can have many ways of solving that, from a minimum norm solution to the MSP, which has many solutions embodied in that one. And you can test among all those solutions using free energy with the Bayesian framework, and you could have the best among all these possible solvers, right? So we have this technical note. In there, you will see many things that I didn't explain in here, which are all the stages that we go to practically solve this. So, for example, we have some spatial filters, temporal filters, how we create the priors, how we optimize the free energy, the algorithm to optimize the free energy. We include all of that in this paper. So if you want to know exactly how it works, we explain it in here. And of course, you can ask us. I can talk with you whenever you want. to explain you any detail of how this algorithm works. Okay, I want to thank all the collaborators to create this talk, and the SPM developers, and many people that have helped me to visit Queen Square every year. And well, all what I've learned, you cannot imagine how much I learned with them. And well, in the right picture, you can see an image from my campus in Medellin, Colombia. Thank you so much.